Hello class. In this video we're going to be discussing lesson 3.2, which is all about translations. So we wanted to answer the question, what are the properties of a translation? And our goal today is to be able to describe the properties of a figure before and after a translation. So recall that we talked about rigid motions, and so the vocab for today would be the composition of rigid motions. So in the previous lesson we discussed translations as part of a rigid motion. So we discussed the different types of rigid motions, and we mentioned that a rigid motion is a transformation which preserves the side length and angle measure of a given figure geometry. And so now what we want to discuss is a specific type of rigid motion, translation. And so a translation is a transformation that maps all points of a pre-image the same distance and in the same direction. So if we want to visualize this, if we have a triangle, say triangle ABC, and we want to translate it, which means essentially what it means is that you're shifting it in a given direction. In this case, you're translating triangle ABC by A units to the right or left and B units up or down. In this case, if you look at this particular example, with this with this picture here with triangle ABC, well then you can kind of see that for A, if you were to take A and move it over, shift it over 1, 2, 3, 4, then it would be 4 units to the left, and it would be 1, 2, 3, 4, 5, 6 units down. And so you can think of it as a translation 4 units left, 6 units down. And so notice that when you translate a given figure from one place to another, that distance remains the same throughout for all of the points. And so if I did this for C, then that would also be for 4 units to the left, 6 units down. And so distances are the same when you're translating. And this is what these saying that the line segments here are all the same distance. And so the symbol for the translation that we use at least in the book that we use for this course, uses it basically uses a capital T, and there's a designation here with these triangular brackets, and this tells you how much you're shifting it. So it's saying you're shifting it in the X direction by A, and then you're shifting it in the Y direction by B. And so in this case, the X direction is left or right, depending on whether it's a negative or a positive number. The Y direction represents up or down motion, which means that it could be a positive or negative, positive for up and negative for down. So another way that we can symbolize this, aside from the notation the book uses, is this notation. This is like the transformation, the arrow notation here. And this is saying you're taking the original point XY and you're transforming it by adding A to the X coordinate and adding B to the Y coordinate. That's another way to represent this translation. And so a translation is a rigid transformation or a rigid motion, and that means that the length and angles are preserved. Okay, so let's look at an example of using a transformation for a given triangle. So we have here triangle EFG, and we want to translate it using this transformation rule. Now remember, the 7 and the negative 4 represent the fact that you're shifting it 7 over to the right in this case, and negative 4 means you're translating it down 4. So because 7 is positive, then this means that you're translating right. Because 4 is negative, you're translating it down. So that's really what it represents. And so another way of saying that is you're taking XY and you're transforming it so that you take the X coordinate and you add 7 to it. Take the Y coordinate, you subtract 4 from it. That's another way of representing that. So let's go ahead and do that. So we're going to take each of these coordinates. So the coordinates of F are -1 and 5. And so we're going to go ahead and take each of those coordinates and follow the transformation rule. So we're just adding 7 to it. So we're adding 7 to the X coordinate and subtracting 4 from the y-coordinate. So we have here 5 minus 4. So then the final coordinate here, -1 plus 7 is 6. 5 minus 4 is 1. And so your new coordinate for f prime is 6, 1. And so really, that's all we're doing here. Let me make this a little smaller. So we have here, we're going 1, 2, 3, 4, 5, 6, 7 units to the right, which is why we got the x coordinate of positive 6. Then we're going 4 coordinates down, 1, 2, 3, 4. And that's really what that represents. And so my new coordinate is what I calculated earlier, which is 6, 1. So that's my f prime, which is now 6, 1. Okay, so now that I kind of showed you that visually, let's go ahead and do it for the rest of the coordinates. So for e, the coordinates of e here are -5, 4. So I'm going to take that, transform into this rule, -5 plus 7, 4 minus 4. So -5 plus 7 is positive 2. 4 minus 4 is 0. My new coordinate for E is 2, 0. Coordinate for G, let's go ahead and do that right now for G. So G is, the original coordinates for G is -2, -1. So we're going to go ahead and add 7 to the x coordinate. Subtract 4 for the y. And so -2 plus 7 is 5. -1 minus 4 is -5. So my coordinate is all the way down here. That's my G prime. I can go ahead and draw my triangle. And that's my transformed triangle. It's basically translated in the same way that the function rule demands. Shifted to the right 7, shifted down. Okay, so now let's look at another example. So this time we want to find the translation rule that maps the quadrilateral STUV to the quadrilateral S prime, T prime, U prime, and V prime. So notice that if you look at F going from S to S prime, well then you're going 1 unit to the left, which means that's a -1. And you're going 1, 2, 3, 4 units down, which means that you're going down 4, which is -4. So remember, up is positive, down is negative. If you repeat that for T, well, that's also going to the left 1, and it's also going down 4. So this is definitely a translation because you're doing it to all the points, and you get the same thing. So we're going to go ahead and write the translation rule. So using the capital T notation and the angle bracket notation, well, we're going -1, we're going 1 left and 4 down, and so that's my translation notation. Doing that for quadrilateral STUV. And in doing so, we get the quadrilateral S prime, T prime, U prime, V prime. So that's one way of writing the translation rule. Another way of writing the translation rule, again, is using the transformation arrow notation that I mentioned earlier. So you're going to take the point XY and you're going to transform it by taking the X coordinate, subtracting 1, taking the Y coordinate, subtracting 4. Either one of those is an appropriate way to determine to write the translation rule in this example. Now we're going to discuss rigid motions that are done back to back. So essentially 2 or more rigid motions. So this is known as composition of rigid motions, in which there are 2 or more rigid motions that you're doing. And the second rigid motion is performed on the image of the first rigid motion. So if, for example, you're translating a triangle ABC left 4 units, up 3 units, and then you do a reflection across line T, well then those are 2 transformations. You're doing a translation, 4 left, up 3, and then the second transformation is a reflection across the line T. So the way we would notate this is, well, we're doing the translation first, and so we're doing the translation on the triangle ABC, so that has to happen first, followed by the reflection across line T. And notice that the sequence of transformations occurs from left to right when you write down the notation. So in this case, because this appears first on the right hand side. That's the transformation that happens first. This is the transformation that happens second. And so you can imagine if you had a third transformation that would appear to the left of the R in this example, so on and so forth. So this circle right here represents the composition operation. This is read as compose or circle. So for example, in this case, you're saying that you're doing a reflection about the line T, compose, and then a translation from, of -4, 3 of the triangle. So you're doing a reflection, compose, and then the translation. Okay, so the order of transformations, as we mentioned, is from right to left. So the translation goes first in this case. So let's look at this example, which is a composition of rigid motions. So in learning a new dance, Kyle moves from position A to position B, and then to position C. What single transformation describes Kyle's move from position A to position C? So we're going from A to B first. So Kyle's going from A to B, which means he has to go to the right 2. He has to step right 2 units, and then he has to step up 2 units, right? So this is going to the right, which is +2. This is going up, which is +2. So Kyle's initial transformation, if this were the point xy, then his new position will change, right? So it's going to be 2 and 2, 2 to the right and 2 up of his original position. And then after that, he's going to go to the right 1, which is +1, and he's going to go down 1, which is -1. So if this is a composition of translations, so he's going to next go to the next transformation, which is what we mentioned earlier, be to the right 1 and down 1. Okay, and that's the sequence of transformations, or the composition of rigid motions rule for this example. And so if we put these together, well, we know that since this is 2 and 2, and this is 1 and -1, well, then that really means that since we know that, so let's go ahead and write down the 2, 2. So if we know that since this is 2, 2 for the first one, well, that just means x + 2 and y + 2, right? That's really what that means. And so if I were to do 1, -1 of that coordinate, which is x + 2, y + 2, well, then that just means I have to add 1 and subtract to the x coordinate and subtract 1 from the x coordinate. So I have to do x + 2 - 1, or I'm sorry, +1, and then y + 2 - 1. And so we have x + 3 and then y + 1 for my coordinates. And so my product here is going to be x + 3 and y + 1. And so we can rewrite this transformation as t 3, 1 of xy. And that's equals x + 3 y + 1. So this right here is my final answer. Know that that's my new transformation. And that really makes sense, because if you think about it, if you were to go straight from A to C, well, then he would have to go 3 units to the right, and then he would have to go 1 unit up. So really, that's what this single transformation represents. Okay, so next we're going to talk about a theorem known as the translations and reflections theorem. This is not really an official name for the theorem. This is just what I call the theorem, and it's just a theorem that basically compares the translations to a reflection. So basically, it says that a translation can be thought of as a composition of reflections across 2 parallel lines. So basically, reflecting something 2 times across 2 lines that are parallel leads to essentially a translation. So if you were to take this first triangle and you were to reflect it about this line, y equals m, well, then you're going to get this triangle right here. And so that is definitely not a translation. That's just a pure reflection. But if I were to take that triangle and reflect it yet again by another line that is parallel to line M, well, then I end up getting the original shape. But this time it gets translated, right? It gets moved here in this case from left to right. So it's the original shape, but translated over. And basically what the theorem states is that the distance that it moves over is actually 2d, where d is the distance between the parallel lines. So if the distance between the two parallel lines were 4, for instance, well, in that case, the distance between the original image, the pre-image, and the final image is going to be 2 times 4, which is 8. So the distance, it will have moved the distance of 8 in this example. And so the way you would indicate this is, well, we have 2 reflections. You're going to do a reflection about m first, followed by a reflection about n, and that's how you would symbolize it. But this is the same thing as doing a translation. A translation in this case can be thought of as a single translation of 2D units. Okay, so let's look at an example. So write each composition of reflections as one single translation. Line K has the equation x equals -3. Line M has the equation x equals 2. And line P has the equation x equals 5. So I'm going to rewrite those. So we know that for this, it's going to be R line K, or line M, is x equals 2. So we're going to do x equals 2, circle, R, and then x equals -3. So really, this means that you're going to be doing this first, right? This is the first one, and then this is the second one, followed by that. So let's just draw what's going on here. So here you have, draw it out here. So we have 1, 2, 3, that's -3. So this is the line x equals -3. It's a vertical line that cuts through the x value of -3. And then we have an x value of 2 for the second line. Okay, so those are my 2 lines. This is x equals -3. This is x equals 2. These are my lines of reflections for this. And so basically we know that the distance between these 2 lines is 5. How do I know it's 5? Well, you can subtract the 2 numbers, right? So you could do 2 minus -3, which absolute value, which gives you 5. Okay, so you can subtract those 2 numbers and take the absolute value, and you get the distance. Or you can just count the distance. So the distance between these 2 is 5. And so I know by the theorem that it's going to take my original shape and it's going to translate it over by 2 times 5, which in the theorem was 2 times d, and d is 5. So 2 times 5 is 10. So it's going to translate it over 10 units. Whatever shape I have, it's going to move over. So this can be thought of as a translation of 10 units x direction and 0 units in the y direction of xy, which equals x plus 10 and y. So notice that the x coordinate is the only thing that's changing here. It's just moving to the right, which is positive. And this is if you were to translate it for -3 first and then 2. Now if we were to do, so this is for part A. So now if we were to do it for part B, in this case you're going to be doing, so we'll write it here. So in this case you're going to be doing, first you're going to be reflecting about equation x equals 5 and equation x equals -3. Okay, so then if we draw that out, so these are my 2 parallel lines of reflection. And remember, we're first doing x equals 5. So whatever shape I have, right, whatever shape I have, I am taking that shape and I am reflecting it across this line. And so it's going to look, it might look something like that if I reflect it. And then I'm going to reflect it again, but I'm going to reflect it about x equals -3. And so what that's going to end up doing is that's going to end up flipping it over this way, right? So this right here will be my final shape. So basically, essentially what we did is we took the original shape and we translated it over to the left, right? And so overall, it moved to the left. And so this represents a negative movement, right? You're subtracting, so basically left is negative. So you're subtracting a number instead of adding it. And so what's the distance that it moves? Well, that depends on the distance between these two lines. Distance between these two lines is given by absolute value. Subtract those two numbers, 5 minus -3. And we know a double negative is positive, so this is really just 5 plus 3. So the distance here is 8. And so now it's going to be twice the distance between these two lines, right? So the distance that this moves to the left is 2 times that number, so 2 times 8, which is 16. And so it's going to be moving to the left 16. And so now I can go ahead and finally say, well, this is the same thing as a translation, in which we take the figure, we move it over to the left by -18 while not doing anything to the y. And this has to equal x minus 18 and y. So basically, we're taking all the coordinates in the original triangle and we're subtracting 18 from them. Alright guys, that's going to do it for the video. I hope you learned something from this lesson, and as usual, I'll see you in the next one.